Yeah, fantastic. So Sarah's at the University of Glasgow, and today she's going to tell us about quantum matched filtering for gravitational wave astronomy. Please take it away.
Thank you. So let me start with a huge thank you to the organisers. I know there's a lot of work that goes into something like this, possibly even more so when it's online. So I'm delighted to be here, and I'm excited about the rest of the programme. I look forward to the next few days. So this project is a bit of fun, really. So I hope you'll indulge me. This project has really just been kind of a nice idea, and just exploring it a little bit. So my collaborators, Chris Messenger and John Veach from the University of Glasgow from our gravitational wave group, reported that for several years they've been discussing over beers at conferences whether quantum computing could help to speed up gravitational wave data analysis. And I should say that they report that these conversations precede even the first detection of gravitational waves, or, of course, having any kind of quantum processor. And so a lot has changed, really, in the last few years. And Fergus Hayes and Scarlett Gow are the two students who've been working on this with us. So I've been to enough conferences in my time to know that occasionally I tune out for a couple of minutes in the middle of a talk and then miss what the punchline was. So I now start all my talks with just to let you know what is the overview, what is the thing that I think is new about the work, and what is the punchline. And so if you tune out a little bit later, which hopefully you won't, I'm fortunate to be on the first day, but if you do, you know what the punchline of the talk is. So the overview, what I'll tell you about in the next 10-15 minutes is the use of Grover's algorithm to speed up data analysis in gravitational wave astronomy. What's new about this? So it's not a new algorithm. It's using a known algorithm, Grover's algorithm. But what we do is explicitly take account of construction of the oracle for Grover's algorithm, without assuming the use of a quantum random access memory, which I'll talk about more later. And we take into account the explicit technical details of actually how gravitational wave data analysis is done in practice. And so the punchline is that gravitational wave data analysis could give us an example of a data analysis problem of real physical interest that could be made tractable with a quantum processor, where we're not assuming, as I say, quantum random access memory. Now, let me be very upfront. This is absolutely not a NISC application. So this is not a near-term application. I'll talk a little bit later about the space and time requirements, but this is really a much longer-term potential application. Okay, so let me start with what is meant by match filtering and why Grover's algorithm perhaps is the right way to go about it. So match filtering is the way in which the gravitational wave people do their data analysis. So what we have as input is a time series of data, which is the response of the detectors to a signal, or just the detector response over time. And the idea is to see whether there's a signal, some kind of waveform hidden within. There's a lot of noise in this, so whether there's a signal hidden in there. And in order to search for this, what they do in practice is test against a number of templates. And so each of these waveforms are potential signals from actual possible gravitational wave sources. And we check the data against each of these templates. And so for each one, you take your data and you take the template and you calculate basically an SNR, a signal to noise ratio, and check whether it's above threshold or not. And we have to do this individually for each of these possible templates until you find one that's above threshold. And so this is a hard problem. Typically, there's a lot of templates, and it's basically a brute force. So you really need to match against every single possibility, or at least order n, before you find a match, if there even is one. And just to give you an idea of the numbers, for the CBC searches, which is a compact binary coalescence, which are the sorts of transient signals that have already been detected, the number of templates we're talking about are 10 to the 5 or more, so upwards of 10 to the 5. And for the continuous wave search, which I'll argue later is perhaps where this could be useful, it's about 10 to the 13 or more. So this rather suggests that Grover's might be useful. So why is it that Grover's is perhaps the right way to go about this? So typically, as I say, there's a very large number of templates and a small number above threshold, and matching is essentially a brute force search. So there are some parts of the matching can be sped up rather, with something like a fast Fourier transform. But typically, matching is a brute force search. And so we know that Grover's can give us a square root reduction in the complexity. Now, I won't describe Grover's in detail because it is fairly standard, so you probably all know how it works, but I'll just remind you of sort of the important components so that I can refer to them as I go along. So typically in Grover's, let me just use the laser pointer. So typically in Grover's, you can think of it in a two-dimensional space. We start with an equal superposition here over all possible values that we want to test. And we think of this W is the superposition of all of those for which there is a match, and the W perp is all of those for which there is not a match. And typically, if there are not very many matches, then this angle theta is very small at the start. Now, the first step is the oracle. So if you can test efficiently whether a particular data value is a match or not, then we can always do this in a way that just gives a -1 to the amplitude for that case. And the effect of this in this two-dimensional space, so we get a -1 for all the terms in the W, and so it basically flips it around this axis. The second part, which is nothing to do with the actual function evaluation, but just a standard part of Grover's algorithm, is to flip about the equal superposition. And the combination, so the final step is going from this blue line to this green line. And the combination of these, as you can see, is a rotation in this space. And so by doing this the right number of times, we can push the state close to the combination of the good matches and find a match with high probability. So what I'll talk about here is the oracle step. So typically when we talk about algorithms that use Grover's, we assume that there is a efficient oracle. So the oracle in Grover's is a function such that f of x is equal to 1 if x is a match and equal to 0 otherwise. And it's often assumed that you can store the list of such values in a quantum random access memory, and then you can efficiently access this. But in the long run, the cost of actually loading that data into quantum random access memory dominates the complexity. And in our case in particular, we can't use this at all because if you've calculated which templates are matches, in order to put them into quantum random access memory, then you've basically done the classical calculation. And so what we've focused on is constructing an oracle for this case of interest. Okay. Okay, so how does the oracle construction work? This is the idea of quantum match filtering. So our first step is to load the data. The data is, as I say, a time series of detector response. It has some length m, and I'll say a little bit more shortly about how long m is. And we choose to encode it in the computational basis as classical bits, so possibly the easiest possible encoding. And so a register of size order m qubits is needed, and a time linear in m is needed to load the data. We also set up an equal superposition over index into templates, so an index register, which stores values from 0 to n-1, where there are n templates that we want to search. So this is initially an equal superposition. In the next step, we generate the templates, and this is the part where we need to take account of how the data analysis is actually done in practice. And it's an important recognition that the signals that make up the templates are well modeled by general relativity. So a closed form expression exists, and we can generate these templates sort of on the fly, if you like. So to generate m points, to generate this whole time series, just needs a time linear in m. And here we have another register of size m qubits. And this is done in superposition. So the register storing the templates is entangled with the register for the index. And now we've got the templates and we've got the data, so we can match against the data. So now we do the actual SNR calculation. This requires the calculation of an inner product and takes time, again, linear in M. And this is the point where the sort of oracle check is complete and we get a minus sign on any of those. Let me just turn on the laser pointer, a minus sign on any of those for which there's a good match. Okay. Now, the diffusion operator, the second part of Grover's, acts on this index register only. And so the final step we need to do is to disentangle all the rest of this with the index register so that the diffusion operator can act correctly. And so the final step is to erase all of these calculations, so erase the calculation of the templates in order to disentangle. And then we apply our Grover's diffusion operator, and the net effect is to push up the amplitude of those states which are a good match and push down the amplitude of those which are not. Okay, so the main thing that's needed is this explicit construction of the oracle, and to recognize that we can do this sort of efficiently, so in a way that doesn't scale with the number of templates. And then the way in which we use this in practice is we use the extension of Grover's algorithm to quantum counting. So quantum counting combines Grover's with phase estimation to estimate the size of that angle theta that I showed you earlier, which allows us to estimate how many matches there are. And there's two ways in which we propose we could use this. The gravitational wave people tell me that probably the most important is just to determine whether there's a signal or not, and then we can just tell the classical analysis, this is where you should look for a signal. And so we use quantum counting to determine simply whether there are 0 matches or more than 0 matches. The other possibility is finding signals above threshold. So we use quantum counting to estimate how many signals above threshold there are, and then Grover's to find templates which match. So let me just briefly in the last couple of minutes give you an example just to show you how this works in practice. And then I'll just talk about some numbers at the end. So this is the first detection of gravitational waves. Again, this is something my colleagues get to show all the time till they're blue in the face, but as quantum computing experts, we don't get to talk about gravitational waves very much. So this is quite exciting for me. This is the gravitational wave signal from a binary black hole system coalescing. So these black holes moving around one another, and the ring down where they coalesce, where they join. This was the first signal detected. It's a very loud signal. Doesn't look like it. There's a lot of noise here, but this is in fact a very, very loud gravitational wave signal. And what's shown here is 28 seconds of data detected at 496 hertz. And so that length of the data is of the order of sort of megabytes of data. And so we did a match of this against about 100,000 templates. So the templates are take 3 parameters in this case: the masses of the 2 black holes and an effective spin. And so each of these shows a slice through a 2-dimensional space for each of those 3 parameters. And all this, I'm showing you here sort of how this works in practice. So these are how the templates are placed in this 3-dimensional space, and the ones that are found at different thresholds. And so this gray dot here is the highest SNR, and the other different colors show you what gets returned if you set the threshold differently. And so with Grover's, what we can do is count how many are above threshold and return one of these templates with high probability. And each of those we could do with the order of about 1,000 Grover iterators compared to 100,000 templates. And just how this compares to the full analysis. So again, this is a slice in the M1, M2 plane. And these are the different templates that show up for different thresholds. And what's also shown here is the Bayesian posterior. So the final step of the analysis, which we think still has to be done classically, is the full Bayesian parameter estimation. So we can determine whether there's a match or not, and then you pass it to the classical analysis to do Bayesian parameter estimation. So the other way I said you could use this was just to determine whether there's a match or not. And this is just to show you what we get in this particular example in that case. So if we simply ask rovers to tell us how many matches there are, then you can see with all these different possible values of the SNR threshold, with high probability, we find that there is indeed a signal in here. So T here is the number of matches. When this is T equals 0, this is a false negative. So it tells us that there's no signal there, even though there is really. And the probability for that is very low. And again, you can estimate this using order square root of n iterations. Okay, so let me just finish up with some numbers. So where we think this might be useful in particular is for continuous wave sources. There have not been any continuous wave sources actually detected yet, because the search is basically computationally limited. I won't go through all the details here because I'm about out of time, but the important number here is about 2 by 10 to the 28. So for a full sky search, for different possible frequencies of gravitational wave signal, different possible locations in the sky, and searching over first derivative of frequency as well, requires about 10 to the 28 order of magnitude, 10 to the 28 templates, which is just not feasible at all currently with classical computation. Now, some of this can be sped up with the fast Fourier transform, about 10 to the 8. And so we're left with a matching step that takes about 10 to the 8 steps, and then a number of templates of about 10 to the 20. And so in principle, a quantum algorithm could speed this up by 10 orders of magnitude. Okay, so let me just finish with the outlook. As I say, this is absolutely not a near-term application. It's just sort of a bit of fun and something that this might actually be useful for in the very long run. So Grover's algorithm and its extension in quantum counting gives us a square root speed up for match filtering for gravitational wave data analysis. Perhaps the most compelling regime may be for continuous wave searches, which are currently intractable with classical techniques. This gives us an explicit example of a data analysis problem, a real one of physical interest that could be, in principle, made tractable with a quantum processor. Now, how big? So this requires, for the CBC case, the one that's already been detected, an error-corrected quantum processor of order megabytes. And for this continuous wave case, it's more like gigabytes. So like I say, this is not a near-term application. And you could think of more sophisticated ways of doing this. Grover's is sort of the most obvious way to proceed. And the fact that the number of templates is so large, but that there may be more sophisticated approaches we could apply to gravitational wave detection. And I'll leave it at that. Thank you very much for your attention.
Great. Well, thank you very much, Sarah. That was really fascinating. Yeah, very exciting. So we do have a couple of questions already on the chat. We have a couple of minutes. So the first one is from Erica Anderson, who asks, how is a good match defined? Could you just tell us that quickly?
Yeah, good question. So it's an SNR calculation in this case. So you calculate the signal to noise ratio, taking into account what we've measured about the properties of the noise. And a good match is defined as one which is above a certain threshold.
Great, thank you. And then we have a second question from David Shaw, who asks, he says, some project that current quantum computing architectures will not provide a practical advantage for algorithms with only quadratic speedup due to, say, error correction overheads or slow gate speeds. And he asks, does your work provide any pointers for how to work around this?
Unfortunately not. I'd love to say yes, but unfortunately not. What we can say is that the step of doing the oracle matching is about the same complexity as would be in the classical case. And we might, of course, expect there to be an overhead in the quantum case, taking into account these things that you mentioned. But then the number of iterations, of course, would still be much less. But no, I'm afraid not.
And just a quick question I had was, so you mentioned specifically gravitational waves, but your general idea would work for many problems of a similar type, or is there something specific about gravitational waves, would you say?
No, the specific thing about gravitational waves is my collaborators.
Okay,
this could absolutely work for other sorts of things. The thing that's needed is that the templates are not numerical, that they're actually, there's an equation, an analytical expression, and you can just generate the templates easily.
great. Well, thank you very much once again. That was a great talk.
Nice to see you.